Okay, let's get down to evaluating some basic logarithms. This is going to go from the relatively simple through to a few more difficult examples, but I promise this actually is not going to get too bad. Let's begin, as usual, with the first one. Log base 2 of 32 says, like every log, what power does this need to get this answer? Now, you may know, hopefully you do off the top of your head, that 2 to the 5th power happens to be 32. If you don't know that, you can count it up on your fingers. 2, 4, 8, 16, 32, 2 to the 5th. But in the interest of answering a few of the later questions, I'm going to write this just for the meantime. I'm going to write it as log base 2 of 2 to the 5th. The reason I want to do this is that logs and exponential functions are inverses of each other. So the fact that these two numbers are the same, the base of the log and the base of the exponent are the same number, that matters a heck of a lot. That means that they're going to make each other go away, and the answer is 5. Now, we knew it was 5 already, but it's good to look at a problem in two different ways so that maybe later on, when it's not clear to look at it one way, we can still look at it the other way. Like in the next one, log base 8 of 8 to the 17th power. Now, I don't know about you, but I do not want to find out what 8 to the 17th power is. That's a very bad number. However, I can use the inverse relationship between these to say that this and this cause one another to go away, and this is 17. Okay? Log base 6 of 1. I'm not going to do the exponential thing here because I think it's easier to say 6 to what power is 1. You should get into the habit of this. Log base anything of 1 is always, right? You say it? Yeah, it's 0. So log base 6 of 1 is 0. And this is true if it's log base 22 of 1 or log base 7/4 of 1. Any log of any base of 1 is always 0. Log base 4 of square root of 2. This is our first really tricky one. Log base 4 of, okay, I'm going to write this as log base 4 of 2 to the 1/2. What I'm going to do is I'm going to try to get it to look like the first couple of problems where it was like log base 2 of 2 to the 5th, log base 8 of 8 to the 17th. Because if I can get this to say that sort of thing, then I've got two easy things to just cross each other out and we'll be done with it. So with that goal in mind, I'm going to say this is log base 4 of 4 to the 1/2 to the 1/2 power. Now, why can I do that? It's because 2, after all, is 4 to the 1/2 power. So I've got 2 to the 1/2. Well, I'm deciding that I will write that instead as 4 to the 1/2 to the 1/2. But now I can use laws of exponents to expand the inside and say this is log base 4 of 4 to the this times this. This is just normal old laws of exponents, not even laws of logarithms. 1/2 times 1/2. And that means this will be log base 4 of 4 to the power of 1/4. Well, now this is the sort of easy thing where these numbers match up exactly. So guess what this is going to be equal to? It's 1/4. Yeah, so log base 4 of square root of 2 is 1/4. All right, that brings us to number 5. Log base 4 of 1/2. Very similar with this. So I'm going to write this first as log base 4 of 2 to the -1. And just like before, this will be log base 4 of 4 to the 1/2 to the -1. That's log base 4 of 4 to the -1/2. And now I've got these numbers that match up, and I can use the inverse relationship between these to say that this equals -1/2. It's not a problem for a logarithm to be equal to a negative number. What you can't do is try to take a logarithm of a negative number. That's off limits. But a log being equal to a negative number is great. That's fine. Number 6, log base 4 of 8. Similar sort of procedure here. I'm going to try to write 8 as a power of 4. Now this is messy, but I bet you can do it. 4 and 8 can each be expressed as a power of 2. Yeah? So I'm going to say this is log base 4 of 2 to the 3rd power. Now, why does that matter? It's because the 2 can then be written as a power of 4. So really, we're making the same sort of dish as before. Look at this, 4 to the 1/2 to the 3rd. And now I can expand that using laws of exponents. Log base 4 of 4 to the 3/2. And this is 3/2. Now, at this point, I want to point out, it's possible to solve these without going through all of these big steps. You can just know off the top of your head that the square root of 4 is 2. And then you cube that and you get 8. So it's possible to know just instinctively that log base 4 of 8 is 3 over 2. And a good math class won't insist that you go through all of these steps, even though you know how to do it faster and you really understand it. So I don't mean that you need to do it this way, but if you know how to apply the steps, it can never hurt. Going on to number 7, e to the power of ln pi. This is the first time that we've had them presented to us in this order. It's always been log of an exponential. This is the other way around. This is an exponential of a log. But the same exact inverse relationship applies. E to the power of ln pi. These have the same base. They're inverse functions, and so they go away. This is simply pi. For the same exact reason, if you have something like this, 5 to the power of log base 5 of 16. The 5 and the log base 5 have the same base, and so it's simply equal to the number 16. I bet you can see what's going to happen with this. We're back in the world of taking logs of exponents, so it's a little bit easier now. ln of e to the 4th. ln has a base of e. So this is, don't tell anybody I'm doing this, but log base e of e to the 4th. You're not really supposed to write that, but it is what it means. The bases are the same, and so these are inverse functions, and we know that this will be equal to 4. They undo each other. They make each other go away. For this last one, I'm going to do it 2 different ways. First is ln of e to the negative 1. Log base e of e to the negative 1. It's negative 1, right? Yes, it is. The second way that this can be done is by applying laws of logarithms. So that you say this will be ln of 1 minus ln of e. What's ln of 1? Log base anything of 1 is always 0. So it's 0 minus, and then ln of e. E to what power is e? Of course, the answer is 1. Or if you like, you can even write this as e to the 1 on the inside, and then you can employ the inverse relationship between them. ln and e have an inverse relationship, so this ends up being 0 minus 1 for negative 1. Of course, if you do the problem 2 different ways that are both valid, you get the same answer both times. Cool, huh?